I'm just going to back up and just make a few comments. Okay, on page 4. On page 4, this diagram is to represent that the fact that given a chemical reaction, the chemical reaction only tells you how something is going to react together. With, in this case, 1 to 1 of bromine will produce 2 moles of hydrogen bromide, and going in the other direction, 2 hydrogen bromide will produce 1 of each hydrogen and bromine. That is not an indication of how much of each reactant could be available, not necessarily. It could be, but not necessarily. And the yellow on these things, the yellow is just to demonstrate that these are actual reservoirs of the 3 different reactants and products, and that, as indicated down here, the number of moles of gas present, and that by the combination of the yellow and whatever the blue or pink is, need not be related to each other in any ratio. So you wouldn't have to have a 1 to 1 to 2 ratio. And if you want to think of it this way, remember in Chemistry 11 we talked about limiting reagent and reagents in excess, right? Well, you didn't have in those cases we were talking about one-way, what did you call it? We weren't talking about equilibrium, we were just talking about straight reactions going to completion. And even in that, we had some that were not in this right ratio. But what this is telling me is that they do have to react in a 1 to 1 to 2 ratio. Okay? So, at equilibrium, for this system that we're talking about here, at equilibrium, the rate of H2 and Br2 reacting is the rate of H2 and Br2 formation. Okay? So you get to equilibrium, and in order for there to be no macroscopic changes, the rate of hydrogen and bromine reacting is the same as it being formed. Okay? And the same is true with the HBr. Okay? Now, are any questions up to that point? Hebden, page 42, question number 8. In the reaction of 3, what's that, ethine, 3 molecules of ethine producing benzene, will the ratio of the concentration of ethine to benzene at equilibrium be 3 to 1? In the reaction, 3 ethine going to 1 benzene, will the ratio of the concentration of ethine to benzene at equilibrium be 3 to 1? We've got one saying no and the rest saying, I have no idea what you're talking about. Well, it looks like the one person knows what he's talking about. Nobody else knows what's going on. Because we just finished saying that it's got nothing to do with the concentrations. It's only got to do with the reaction rate, or how something reacts. Okay? That's what that picture was all about. Had nothing to do with the concentrations. This is a reaction mechanism. It only tells you how it reacts. Okay? I know.
Why wouldn't that be?
It need not be. That's the point of this. This is the same thing as saying, like this, what we're seeing here, these bars, this is just the reaction mechanism. It's not saying anything about how much is actually present. The question here, you have to read the question carefully. I'm thinking you have to actually read this carefully, because what it says in this reaction, will the ratio of the concentrations at equilibrium be 3:1? No! We just talked about that here. Got nothing to do with it. This is going to be interesting. Okay? Is there any questions then?
Yeah, is there like a mathematical calculation to figure out what it's going to be?
No, you can't, because like going back to the example of me having 3 different taps feeding into one reaction chamber, just cranking them all out and filling it with a combination of hydrogen bromine, and hydrogen bromide, all in there. You don't know what it's going to do, but you do know it's going to react like this. But you don't know what the concentrations are. You have no clue. Okay? That's the whole point. The whole point is that when you're talking about something like this, that only tells you the ratio of reaction. It has got nothing to do with the concentrations, the possibility of having odd concentrations. Okay. Well, moving along. Spontaneity. Thank you. What's the color that we're supposed to be doing this? No, this one's 2.1, 2.3. This is predicting spontaneity for this. And for this spontaneity, it is orange for the, when we say something is spontaneous, what we mean is that a change without outside assistance Okay, spontaneity in chemical systems is determined by 2 things. Number one, first thing that it is. Oh. Okay, we're talking about spontaneity of systems, like the spontaneity of, say, this system here. There are 2 things that govern it. The first is enthalpy. And you've already kind of met this guy. This is the energy Enthalpy, yeah. Or heat. Okay. This. Hey.
Is enthalpy
Yeah.
or AL?
AL. Enthalpy. Enthalpy.
We agree. So that's a factor in spontaneity. Wouldn't that be the very thing that would be the existence of making not spontaneous?
Say again.
So it says it's spontaneous, spontaneous to change the outside system. But if there's two factors that cause spontaneity, are those in that system?
No, you'll see what we mean. It's to do with what kind of reaction it is, whether it's an endothermic or an exothermic reaction to begin with. Okay. The other one is entropy. And that has to do with the degree of randomness. And when we're talking about randomness, we're talking about the difference between something being, say, a gas, a liquid, or a solid, or number of bonds, or the number of product or reactant molecules, okay? Okay? It's better explained on the next page, so don't get your hair in a bun. Okay? Are we okay with that? Okay, so here's the explanation. Enthalpy, or H. See, I told you you've already met this guy. Enthalpy So here we have an exothermic and an endothermic reaction. So this is exothermic. And this is endothermic. And basically, if you think about the energy hill as something that you have to roll a rock off, so what I'm trying to make visually memorable for you is that the side having the minimum enthalpy is favored. So when we're talking about these energy diagrams, the reactant side is always on this side and always goes to products. So if the reaction is exothermic, that means that the products are favored. What does that mean? That means that if all else is equal, this reaction will go as planned from reactants to products. It'll just automatically go that way. If it's endothermic, it will automatically favor the reactants. In other words, it won't go readily. Okay? Yes, sir.
So enthalpy is measured from the lowest point, or where is enthalpy measured from?
Basically, enthalpy is a measure of delta H.
And so would the reactants in the exothermic not have zero delta H? They started that line and ended that line? the products go down?
I'm sorry, tongue here, going this way. The idea is that this will go from reactants to products readily.
What would the delta H of the reactants be?
Oh, it's not the delta H of the reactants, it's the delta H of the reaction per se, because it's an exothermic reaction. Okay? So if there is a net loss of energy, then it will favor the product side. Whereas if you're talking about an endothermic reaction where you have to put energy in to make it go, it won't be spontaneous just if everything else is equal, because it's like you're constantly pushing something uphill. So it'll favor the reactant side. Yeah.
Can you explain the phrase, the side having the minimum entropy is favored?
The minimum enthalpy is whatever the energy is.
Okay.
Delta H is really the change in enthalpy.
The lowest?
Yeah, in the system, yeah.
Okay.
So for this one, the exothermic, you're starting with reactants that have a high, the reactants themselves have a high degree of enthalpy themselves, and by the end of the reaction have low. So the delta H, or the change in enthalpy, is what we get out. Okay? So I'm sorry if I confused you with my terminology. Sorry about that. But so the side with the minimum enthalpy in either one of these is the side that's favored, so far as the energetics is concerned. Okay? Now it's not. You'll see that's not necessarily so. That's going to happen. Okay? Now, entropy is the degree of randomness, and the rule is that whichever side has the highest degree of randomness, this is favored.
That is
You'll see. You'll see in a minute.
entropy is favored.
Entropy is favored. Yeah.
So what?
Is randomness kind of a bad thing?
I don't know. So down below in the box, I've kind of like encapsulated it just in a simple rule. So the tendency to minimum enthalpy is favored, and the tendency to maximum entropy is favored. Entropy is where gases have much greater entropy than solutions. Which have much greater, or not greater, these are getting somewhat close to liquids.
Greater what? Greater entropy?
Yeah, I'll put another little thing on the bottom here. So down in gases here, this is greatest S. S is the symbol that we use for entropy, and this is lowest entropy. Okay, so if, for example, if I had a solid and a solution on one side and gas on the other side, then the maximum entropy would be on the gas side. Okay.
What's the double greater than sign?
The double, this means very much greater than.
Very much greater.
Solutions and liquids are kind of like in the middle, where they have, solutions are more random, because what you're talking about is you're talking about an aqueous environment and ions floating around in it. Okay? Whereas a liquid is the same molecule just moving past each other. Like if you have benzene, all you've got is benzene molecules. That's all you've got. If you've got a solution of, say, sodium chloride, you've got water, you've got sodium ions, you've got chloride ions. That's far more. Miss Gregory, did you? Yeah, come on in. Just yell at me.
I don't really like yelling at you.
Ah, no, it's all good. These guys do.
Accommodations guys, did they know they were did you tell them they had to be here for this?
I didn't have anything to do with that. That was Mr.
So they might
I didn't
not
even
know
know.
about it?
I didn't even know.
Okay,
I didn't even.
so I was just wondering if
Yeah.
he
No.
was legit not known. So
Yeah,
maybe
I
all the
was-
kids in your class didn't know.
I didn't know that there was today either.
Thank you.
I only found that out this morning.
Well, I just got an email currently and just so thank you. Sorry to interrupt your class.
That got past me myself.
Thank you.
Okay. So solids have very, very, very low entropy. In other words, they're very highly organized. So we'll do a couple of examples to make it plain, okay? Let's do this. Let's turn the page. And I've got a couple of, I've got 4 examples here. So example number 1 is at the top of the page. We've got calcium chloride, which is a solid, and we have got water, which is a liquid, okay? And you combine them and you get ethine, gas, and you get calcium hydroxide, which is aqueous. So now, based on the helps on the previous page, which side has the highest degree of entropy? Very good, the right side. So that's why, what we're comparing here is gases and aqueous solutions which have a higher entropy than a solid and a liquid. So that is why the overall reaction should spontaneously go this way, all things being equal. Mr. Pree.
So what would happen if you had gas and a solid on one side and an aqueous and liquid on the other?
We'll get there. Okay?
Also, I have another thing. For that equation up there, it says there's like chlorine on one side and then carbon on the other. And it's like,
Oh, what do you know? Don't worry about it.
oh, well, that seems legal.
It's maybe a little bit illegal, but what it is, it's just demonstrating the difference in the different phases of which would be favored. Okay, what a good point. Okay, example 2. You have
You answered why? In example 1?
okay. In this situation here, what?
Did you answer the why?
Of what?
Example 1, did you answer why?
In color, in living color.
Okay, so no, you didn't answer. Thank you.
These guys are so lockstep. Cross all the T's, dot all the I's. Okay.
Get Doc marks if we don't.
Yeah, right. Okay, you've got A, which is a gas. You've got B, which is a solid. You've got C, which is a gas. And you've got D, which is a solid. Which way, and you can see that it goes in this direction. Why is that? Yeah,
Because there's more gas on the right side.
that's right. You've got 2 moles of gas on this side and 1 mole of gas on this side. This is the more random or the greatest degree of entropy. So that's why it's going in this direction, is because you've got 2 of gas and only 1 gas on this side. Okay? Let's look at the next one. Example 3. Now we've got two things coming to play here. We've got enthalpy and entropy. Okay? So, let's look at enthalpy first. Enthalpy is the energy. So is this an exothermic or an endothermic reaction? Yeah. It's exothermic. So that means, thank you, that means that enthalpy is pushing it in this direction. Okay? What about entropy?
Enthalpy or entropy?
Entropy. S. Because we're looking at liquid here, and we're looking at 3 moles of gas here. Entropy is pushing it this way. So we've got basically a tug of war going on. In this situation, we have got equilibrium. This is going to be an equilibrium situation because entropy is going to drive it one way, enthalpy is going to drive it the other. Okay? This is equilibrium. Offsetting
Entropy?
offsetting enthalpy and entropy drivers. Do the next one. You guys do the next one. You know what you're doing now.
So what is example 3 do? This is the 2 gases on one side, but then we're going to be more of that side because we increase
I don't know.
What is non-equilibrium?
Which way is it pushing?
That's when we push over here. So you guys could be raising.
Which way are you talking about? You're talking about example 3 or example 4?
How are we doing example 4?
You're doing example 4.
Okay. So there's equilibrium. What are the other overall tendencies possible? Non-equilibrium?
Favors products, favors reactants.
Okay.
Yeah.
So it says that example 3 is at, or it says equilibrium.
Yeah.
Does that mean it is at equilibrium or it can achieve an equilibrium?
It will go automatically go to an equilibrium situation.
Okay. And so all the other ones will just go to completion?
Depends.
Examples 1 and 2?
Probably. Well, look at this one here. The one that you just did. What's the outcome of this one? Yeah, why? 2 reasons.
Basically,
Yeah, go ahead, Ms. Dietrich. Very good. So entropy favors this side, right? And it's exothermic. This, you guys should recognize this now. This is the combustion of methane. So you add a spark and you got a burn going now. Okay? So in this case, both are pushing that way. So overall tendency toward products and completion. Only that the likelihood is this is going to go to completion. Oh, sorry, dear. Yeah. There's another one on the other page, next page. Check that one out too. Okay, we are at, oops, sorry. Okay, what's the story on example 5? I'm sorry, say again. Yeah, it's going to favor the reactants, okay, for two reasons, yeah? Enthalpy-wise, what is this? What kind of reaction is this? This is endothermic because I'm adding energy here. So that means that enthalpy is pushing it that way. Entropy,
So what actually is that reaction? It's silver and the oxygen,
okay? No, this is gold. Yeah. Gold and oxygen. This is adding heat to give you oxidation of gold. Well, you and I know that gold is not readily oxidized, right? Well, guess what? That's why. Yes, sir.
So, can it be said that gold oxide will gradually go back to gold and oxide?
You can.
If I have gold oxide, could I keep it?
Say again?
If I have gold oxide, could I keep it?
If you want it, you can have it.
Or would it turn into gold and
Not spontaneously. I'm pretty sure you have to do some kind of process. But like the overall energetics of this, to make that a reverse reaction, you'd have to still get over an energy hill of some sort, I'm sure. Okay? Overall tendency, this would be considered a no reaction. That is, favors the products. I'm sorry. It's been a long day.
Tell me about it. We should have a nap.
If I have a nap, I'll never get up.
ever?
Probably not until tomorrow morning. I was awake at 3:30. So. Yeah.
Like 8 a.m. tomorrow morning? So you can see if you're reading studies or?
Uh-huh.
Excuse me, what does no reaction mean?
If I was to add these together, the chances of it going is that it won't. Yeah. Okay. Finally, my favorite part of this entire chapter is Le Chatelier's principle. It's a dying. If a closed system at equilibrium is subjected to a change, processes will seek to reestablish equilibrium. Now, we've already seen that. We've already seen that, because remember when we did that big graph where this theoretical situation had a calculated KEQ value of 5, and even when I injected it full of the B, the product, it reestablished at concentrations whereby the concentration of the products divided by the concentration of reactants came out to the same number again, 5. Okay? That is what this is saying. Okay. In order to do this, I'm going to divide it. I'm going to try to model it on the board, and then I'm going to we'll come back for the sake of our video. What do we call it? Our video land. They'll be upside down. It doesn't matter. Okay, please don't let the charge symbols throw you off, okay? Equilibrium is a lot like a bit like a teeter-totter. Now, as we saw before, concentration does have an effect. Now, oh, sorry, this is a lie.
It goes the other way?
Okay, so if you imagine the yield signs as like the pivot point in the teeter-totter, the question would be, what effect would occur if I change the concentrations of the say the iron 3 plus ion, the thiocyanate ion, or this ion here? It's basically what would happen here. So if I increase this, please imagine this with me, okay? If I increase this, I would be basically pushing this up, pushing this concentration up, and equilibrium is going to go to this side. Okay? In other words, the addition of iron ion, that means it's going to, more of that is going to combine with the thiocyanate ion, and it's going to push it this way. Okay? Now, I'm not asking you to understand what I just did. What, at this point, in the beginning at least, I just want to get you thinking of how can I predict, what strategy can I use to predict what's going to happen. The same thing is true if I was to instead increase the ferrous thiocyanate ion. If I was to increase that, it would be basically like bumping this up, and it's going to tip the scale, and more of this is going to decompose, and we'll get more here. So if I increase the side, it's going to cause it to slide together the opposing side, okay? Same thing as here. If I increase this, it's going to slide this way, increase back and forth. Now, what would happen if instead of increasing the concentration, what if there is a way to pull one of these ions out of solution? Yeah, it's going to be the same thing. Suppose I added sodium hydroxide to this. Well, what's going to happen is the OH is going to bind with this, and it's going to pull this out. It's going to pull it right out. It's actually going to make a solid. But what it's doing is it's pulling this out. So basically what's going to happen is I'm going to pull this out like this, and so what's going to happen is more of this is going to combine and produce more ferrous thiocyanide. Okay? Same thing on this side. If I was to somehow, say, throw in a chloride ion in here, iron chloride will be pulled out, and it's going to go like this, so it's going to move in this direction. Are we okay with these ideas? Yes.
So can you add just iron, or do you have to add both iron and the other guy?
No, you can add, if I wanted to just add iron to this thing without affecting these guys, without adding thiocyanate to here, iron nitrate. Because the nitrite ion isn't part of the system. It's what they call a spectator ion. It just sits around, does nothing, it's pretty. Okay? But so what's going to happen is I'd essentially be bumping this with iron, and it would go that way. Yeah.
But, so if you did that, would the reactant side be lacking in BS or SCN?
Yes.
Okay.
Yeah. You can push it one way or the other. Okay?
So the concentration on the reactant side won't always be 1:1 from iron to SCN.
No.
Okay.
No. Because I've added some.
Okay.
And some is taken out, some is just taken out. Yeah, it's going to change it. But that's the idea, is that it's going to, the whole idea of the Chatelier's principle is that it's going to seek to reestablish concentrations, which when you divide one by the other, you end up with the same, what do you call it, KDQ value. Yeah.
So how would you calculate the concentration of iron plus SCN?
Oh, we'll do that. Hold on. Just keep your shirt on, buddy. It's coming. It's coming. Okay? On the notes, if I was to decrease Fe3 plus, that's going to pull, if that's the pivot point, it's going to pull it down, it's going to shift to this side, and so what's going to happen is that and this is the important part, the Fe3 plus and the SCN negative is going to go up. The concentration is going to go up because it's falling to this side, and the FeSCN 2 plus ion is going to go down. It's going to drop. That's the important thing. In your mind, you have to see the balance being tipped, but you have to also interpret what's going to happen. It's sliding to that side, so that's going to be used up to make that. Okay? If I increase SCN, it's basically pushing up, and so you can figure it out that in this case Fe3 plus and SCN is going to go down, and the opposite's going to happen with the Fe. It's going to go up. Increase the FeSCN, tipping it this way again, and I'm not going to bother writing it down because you can figure it out now. It's the same as the top one. Okay? Now temperature depends on whether it's endothermic or exothermic. In this case, what? I'm sorry? No, okay, what this is that if I have a system that is at equilibrium, this is the important part. In the box above, if you have a closed system that's at equilibrium, it's already at equilibrium, okay? It has to be at equilibrium, and then you try to do something to it. It's going to change. You're going to change the situation. But what it's going to do, it's going to try to reestablish equilibrium again. Okay? Yeah. Yeah. Now, that is off on the left-hand side here. Delta that means that these are different ways of doing it. Changing the concentration. So this is, the first type is changing the concentration. Okay? The second one down here is changing the temperature. And again, this depends, well, whether it's an endothermic or an exothermic. In this example, because the 76 kilojoules is on the product side, that means that this is exothermic. So, if I increase the energy, if I increase the temperature, it has the same effect as basically pushing this up. If I push this up, it's going to shift everything to this side. And by now you can see, oh, well, if that's what's going to happen, I'm going to lose NOCl, and I'm going to gain more NO and more Cl2, because it's going to be translated into this. If I cool it, that's the same thing as pulling energy out. Or, I'll do it blue for cool. If I pull it down like that, then again it's going to tip in this direction. And more of the NOCl is going to be produced from the chlorine and the nitrogen monoxide. Yes, sir?
Is this kind of using the specific heat capacities? With only so much heat being produced or held on one side? When
I don't know if it's got a bearing on specific heat capacity.
If when you remove the heat, it allows more heat to be produced? Or will that reaction just continue to heat up, heat up, heat up?
I don't know. For me, my understanding of specific heat capacity, similar to yours, is that it's just how much heat can an item hold and maintain 1 degree Celsius change. I don't see the link between the two, but I'm not saying there isn't one. Okay, I don't see it. So are you guys okay with these two ideas? Say again? I've got like lots of arrows there. I'm not sure I understand what you're saying. Oh, if the temperature's increased, if this is an exothermic reaction, okay, that means it's liberating heat. So if I put more heat into it, basically what I'm doing is heat is getting in the way. Because in this case, heat is a byproduct of the reaction. So if I'm adding, it's almost like adding garbage to a situation. I effectively push this up. Like, I'm pushing it up, and it's causing the equilibrium to shift towards the reactant side. So that means that NOCl is going to be become NO and Cl2. Okay? If I cooled it, this is an exothermic reaction, so if I cool the system, what that means is effectively I pull this down and it shifts this way. That's the strategy. What that means in real life is that if I have an exothermic reaction and I cool it, it makes it more efficient. Okay, within reason. Okay, I don't want to start getting into collision theory and kinetics at that level. Okay, so are we okay with it so far? Okay. What? I've got another change in concentration, it looks like. Okay, I'm going to I'm not even going to bother doing the top one because you guys can figure that out because that's another change in concentration. But what I want to do is I want to look at this one here, change in pressure. And so change in pressure only exists if you have gases involved. So change in pressure. I don't know. When I was a kid, we would go to the P&E, and we would get these balloons that were like about, what's that, 4 feet long. They're huge balloons, and they were hard to break. They weren't the type that if you got close to anything, it's going to explode. They were really, really resistant. They'd last for months. I want you to think of those balloons in this application because the teeter-totter doesn't work in this strategy. Let's look at what we have here. Okay? In this system here, we have 3 moles of gas on this side, and we've got 2 moles of gas on this side. Okay? So what I want you to try to imagine is I have a balloon. One of those big long sausage balloons. Like this. Now, there's a reason why I did it lopsided, because this thin part represents the 2 moles of gas. This side represents 3. Okay? Now, this is a system, okay? This entire system, so I've actually got a total of 5 moles of gas in one container. Okay? Now, the question is, what happens if I increase the pressure of the system? You had your hand up first. Is that what you thought? Yeah. The reason why I drew it this way is that if I had one of these sausage balloons, you have to imagine it, that if I put pressure equally, because this is in one container, if I put pressure on it equally, what side is going to respond first? It's the bigger side. Okay? So what's going to happen is you just imagine it go squishing it over the other side. And that's what happens. That's the way it goes, man. Okay? So if I increase pressure, no, I shouldn't do that. how am I going to do this? Yeah, I'm going to say, I'm going to squeeze down like this. And this is increasing pressure. Then what's going to happen is it's going to squeeze this way. So that means that the product side is now going to be favored. Okay? Now, the flip side is what would happen if listen to this carefully. What would happen if I increased the volume? Pressure decreases, right? So that's the same as me grabbing the balloon and pulling it this way. What's going to respond first? The 3 side again. If I pull, and think of it this way, if I increase pressure and I squeeze the 3 this way, if I do the opposite operation, what's going to happen? The opposite, right? Oh, come on, it's not that hard. It's not that hard. It's easy. Yeah.
So, theoretically, will you get stuck at 2.5 on both sides, or will you just keep squishing the balloon?
No, this is just a strategy to try to explain what happens. This is something that to be honest with you, what you see here, these little diagrams and all those things, I did this myself. I had to think, like, look, when I was in high school, I only took Chemistry 11, and I sucked at it. I never did take Chem 12. When I went to university back in the 70s, I got through what was the equivalent of Chem 11. Chemistry 12, I sucked at it, okay? It wasn't until I go to university out here that the coin dropped and I understood it, and I got it. But that's different than trying to teach. Like, there's a big difference. Like, there's a saying that if you want to know how difficult the English language is, try teaching it. If you want to know how difficult Chemistry 12 is, try teaching it. Frick. You think you guys got it tough. I'm like, what? Really? And so I had to come, because my students would sit there, when I first started doing this, students would look at me and say, what? What do you mean? How does that work? I don't really know. Well, then you're not much of a help. I know I'm not much of a help now. But this strategy, for me, I get it. Like, I haven't taught this in 2 years, but even before I open my book, I understand this. I get how it works. Not necessarily why it works all the time. Like, I don't quite understand why this works, but this strategy explains what will happen, what to expect will happen in this system. So, hey, if I don't understand, fine, I'm okay with that now. But at least I know what's going to happen, okay? So if pressure is increased, it's going to favor the products. So it's going to go to the products. And if it is decreased, it's going to go to the reactants. Okay? Now, the last thing, which it's kind of funny that they put it in, but I'm going to do this with a little bit different color because it's a bit of a red herring in my mind. A catalyst does not have any bearing on where, if one side is favored or the other side is favored. It has nothing to do with it. All it does is it gets you there faster. That's all. Okay? You're going to get to the same point. You're not going to change it back and forth. Yeah?
So does that mean that coffee is a catalyst for humans?
No, it's a fuel.
But
There's a difference.
We're going faster. It doesn't matter if we're going somewhere good or somewhere bad. Exactly.
I'm just going to see. Okay, I want to, the last part here is, as far as I can see, I'm pretty much done the first part of, I'm not going to go into the calculations today. Calculations we're going to leave until Thursday, because I don't want to overextend. But I do want to spend a minute just looking at practical applications. You guys have probably heard of this guy before. Have you ever heard of this guy by the name of Franz Haber? Or Fritz Haber? Yeah? Do you guys? It talks about prior to First World War, there was an issue. The Germans needed nitrates in order to make explosives. But the problem was they got their nitrates from Chile. And the issue was that they were blockaded, naval blockade. They couldn't get the nitrates in order to make their explosives. So this guy by the name of Fritz Haber took on the challenge of how do I make nitrates? Well, this is basically the idea here, is that he knew that nitrogen and hydrogen could combine to produce ammonia. Now, it turns out that ammonia is the first step in making the nitrates. And this is the part that really got to them. You see, nitrates you could mine nitrates, but you could also get it from bird drop, it was guano. And in some parts of the world, there are ginormous deposits of it. Anyway, so the issue was that somehow they could do this, they could produce this, but somehow they had to maximize it, because you notice that it's an equilibrium reaction. So the big question was, how is he going to do this? How is he going to maximize the available nitrogen and hydrogen? Well, look at it. What do you think?
Okay, what are we trying to get?
The most ammonia out of the situation as possible.
Most ammonia?
Mm-hmm.
Okay.
Yep.
Pretty good.
Well, there's going to be you're going to have to play with the temperature for sure. Now you have to be careful with the temperature though, because you still have to make activation energy. But you're right. There was a cooling part of the process in order to pull it to that side. What else could you do in that? Yes.
High
Pressure,
pressure.
because you've got 4 moles of gas here and 2 moles of gas here. So this was done under pressure, high pressure, and once we're getting to reaction, lower temperature. Anything else? What if he could find a way to remove the ammonia? Mm-hmm. They tip it more that way too. Yeah.
Shouldn't you also inject hydrogen gas into the system?
Yeah, you could increase both of these. You could decrease this. You could cool this. You could pressurize it. And it turns out that he did a combination of all of those things. But there was an issue. Apparently there was an issue with the temperature. And that's why I think it says in this one here, in order to get to equilibrium initially, he had to initially start at a high temperature, and then once he was there, and it was reacting, then it was cooled. But in the initial going, he had to get it up over the energy hill, and then once he could do it, because nitrogen is the only way you split nitrogen is either with lightning flash or certain bacteria. Okay, so he had quite a problem, but he managed to do it, and it became known as the Haber process. Okay, now, so in your notes on page 8, there are two practical applications. One's the Haber process, which we just chatted about, and the other one is how do you make concrete or cement. Okay, now I'm going to call it right there. It's late in the day anyway, but when we come back, I'm anticipating that Thursday. What's today? Today's Tuesday, yeah?
Tuesday.
Okay. Thursday, we're going to go big into calculations. Thursday is a day you do not want to be away. If you're away Thursday, you've got a serious issue. No, I can't afford any study blocks. We cannot afford study blocks. We do not have room for study blocks. Okay? If we had room, I would have made this a study block. We don't. Okay? So,